So my name is Juan Senga. You can call me Juan. I'm a postdoc with the Center for Energy and Environmental Policy Research, and I'm also affiliated with the Climate Policy Center. So today I'll be talking about some of the research that we've done on modeling data center flexibility. So Shahui a while ago talked about data center flexibility from the perspective of just I want to say like one data center and how that's being managed. Um, and he mentioned a while ago that the work that I've been doing over the past, I want to say, 2 to 3 years, have really been dealing with policy and entire system. So the U.S. system, in more specifically. And I first want, before I dive into this presentation, which will be the meat of the talk, I want to address some of the questions that were asked a while ago in Xiaohui's talk about what are the things that the grid is doing to address this growth in data centers, and how are utilities and states really trying to approach this problem. And I think um, understanding that and then going into the flexibility portion would be good for us, just so we'll have this mindset that okay, like it's not like all of these utilities and ISOs and RTOs are just taking things and watching from afar. They're really trying to engage with data center owners and data center providers. So bear with me. This presentation was given in like October 2025. So I just brought it up because of the questions a while ago. So I might miss some points. And also some of these points might already be outdated given a lot of the progress that's happened like over the past few months. But I think essentially there is a big push from the federal government around, uh, you know, the U.S. being um, a dominant player in the artificial intelligence race. And there's a lot of things that they're trying to push for in terms of policy to accelerate permitting, to accelerate the efficient build out of more infrastructure, not just in terms of data centers, but also other parts of the grid that would be helpful in facilitating the build out of data centers. Um, on the part of ISOs and RTOs, there are some proposals from the perspective of these ISOs and RTOs around being wary of the increase or the fast, increase in data center load. And what they've been proposing is really all about um, the ability for data center or for the ability for these utilities and RTOs to curtail some of the data center load in times of uh, you know peak requirements. And naturally, data center owners are very averse to that. They've sent out these um, public, I want to say, documents going against some of the proposals. And I believe the non-capacity backload proposals of PJM have been shut down, or at least they've been revised, so that it's no longer a requirement but a voluntary thing. So you can see how powerful some of these data center owners are in pushing for certain types of policies. Um, some of the ratepayers are, of course, uh, happy when it comes to being able to regulate the connection of data centers and how they're going to be connecting to the grid, because of this notion that there might be an increase in data center load might lead to an increase in electricity prices. So what we're saying is there are many different viewpoints that are sort of um, in, I want to say, in conflict with each other. Or not really in conflict, but they have very different goals, I want to say. From a federal perspective, they want to use or build data centers as fast as possible, and they want to power these data centers using their preferred sources of energy. And how they're doing this is they're, you know, giving out loans, grants, incentives. They're changing the regulations around environmental review so that there are going to be expedited approvals. Um, and they've reversed some of the previous administration's executive orders, which require renewable energy resources to prefer, let's say, natural gas, nuclear, and coal. So that's the federal viewpoint. Um, and as a result, there's this pressure from utilities and RTOs and ISOs to invest in a lot of these generation and transmission upgrades so that they'll be able to keep their costs manageable and to maintain reliability in their systems. And really, what their approach here is or their solution to this is two things. One is tariff design, and the second is interconnection management. And I'm not. I mean, I mentioned this isn't going to be the meat of my talk. I just wanted to show this to everyone. But there are tariff designs that are starting out in some utilities, which are already being copied by other utilities all over the country. So you have here some example tariffs from different companies. You have here the different components of this tariff, the qualifying loads, the contract durations, the minimum demand charges, exit fee conditions, and some collateral that data centers have to put in. So these are ways that I hope would answer some of the questions a while ago. So this is for this part of the presentation, and I hope that's good. So let me go now to my actual presentation. Any questions about that before I move on? Okay, right. So let me move to my actual presentation. So again, I'm Juan. I'm a postdoc working on power systems modeling with CEPR and the Climate Policy Center. I've been working on capacity expansion models in the US and in Southeast Asia for a couple of years now. And I'm going to be talking about how we model data center flexibility in the US grid. And I always want to start off my presentations about our research by recognizing some of the folks who have done great work in putting out this research to the world and presenting it in many different places. So we have our principal investigator, Professor Chris Knittel of Sloan, CEPR, Climate Policy Center, and NBER, and my colleague, Dr. Shen Wang of CEPR. So this work that I'll be presenting is available as a working paper in the CEPR website. It's a project that's funded by the Future Energy Systems Center and the MIT Energy Initiative. So I I might be a bit biased. I think it's a great paper, but you tell me. We can have a discussion, and that'll be a fun conversation to have. So, in the next hour or so, maybe around 50 minutes, since I spent a bit of time a while ago talking about policy and tariffs, um, what will we be covering? So, we'll be covering mainly two things. The first one is on what is data center flexibility from the perspective of a system level grid, and how do we model that type of temporal flexibility? And I want to say we're going to be focusing on temporal flexibility here. And the second one is the results of our research, so the fancy stuff, right? What's the impact of data center temporal flexibility on the grid? And this presentation is going to come into two parts. The first one has a little bit of mathematics, some modeling, but I swear I'm going to try to make it as digestible as possible. And I feel like that's also practice for me in trying to explain what our research is about. So please bear with me on that part. And the second one, maybe what you'll all be more interested in, but we'll get there eventually. So when we talk to data center providers and data center stakeholders, they've always been saying that data centers can be an asset to the grid. And Xiaohui a while ago talked about that. I'm sure over the past week, there's been all these conversations around data centers as assets. And what everyone has been saying about this is there are ways for data centers to move their computational load from one R or the other, or one region to another, in order to take advantage of cheaper electricity, right? And why is there a conversation around this? Well, it's because of it's because of the capacity utilization of data centers. So here is a graph from, I think, LBNL. Yeah, it's from LBNL. Looking at the historical utilization and the forecasted utilization of different types of data centers, right? So x-axis, what you have here is the years from 2014 to 2028. Y-axis, you have the percentage average capacity utilization for a data center. So you see that the AI inferencing, the AI training, the hyperscalers, they're operating at roughly an 80%, 40%, 50% capacity utilization. So there is that headroom of around 20, 40, or 60, depending on what type of data center you're going to be looking at. And if we look at this from at a more granular level, you have here the capacity utilization on a daily basis of an AI-focused data center and a general-purpose data center. So AI-focused data centers hover at around the 80% capacity utilization range, and their fluctuations aren't as big, right? It's still, the variance is still quite small. Whereas general purpose data centers, you see that the variance is quite large, right? But nonetheless, because the growth in data centers are really all around this AI training and AI data centers, we can, at least from our assumption, we can more or less look at the AI-focused data centers. So this is also what data center owners are looking at, and they're saying, well, we can say that if we provide flexibility from a data center's perspective, we can reduce our cost because we can take advantage of cheaper power, and we can also provide co-benefits to the grid of emissions reduction, right? Because more often than not, the cheapest power, in some circles, the cheapest power is solar and wind. So they're saying we can find when the sun shines the brightest or the wind blows the strongest, and we can move our load there, and therefore lower cost, lower emissions, everyone's happy, right? But is that really the case, right? That's the big question that we wanted to ask. Is that really the case? If data centers do provide this type of flexibility, and they have this, for lack of a better term, a mandate to look for the lowest cost possible, will they be actually providing that co-benefit of emissions, right? And this is not just me, talking about this in terms of, oh, are there really companies doing this out there? Well, there are, right? So Google is one of the prominent ones that released statements over the past couple of months saying that they're making their data centers more flexible in order to help out the grid, in order to fulfill their 24/7 carbon commitments. Oracle and NVIDIA also doing the same thing. They're trying to power the data or make their data centers flexible because what they're saying is they can both provide cost reductions, not just for themselves, but for ratepayers, and also they're going to be able to improve, their emissions output. So we're in this situation where flexibility is really coming into play, and we want to understand if what these companies are saying is really what's going to happen, right? At least theoretically. There might be some policies that may be implemented that will make it more feasible and whatnot. But, as of this moment, based on the data that we have, what's really going to happen? So, how do we do this? Well, what we use here is what's called the MIT GenX model. So I believe over the past week you've learned about the TEPES model, if I'm not mistaken, and macro. Yep. So GenX is the predecessor of the macro model. So it's essentially it operates in a very similar way. It's a large-scale capacity expansion model, which takes in inputs from a variety of resources, everything publicly available, forecasts from government institutions, educational institutions, and publicly available reports. And I want to say that this is used in a variety of peer-reviewed publications and reports, both within MIT and outside MIT. So talk to a random person in MIT or CPR, and more likely than not, they would have used GenX at one point in their research. So just so I can prove that we've done quite a bit of work on this. So this is some of the recent examples of policy analysis and research papers that our group has been working on, mostly on transmission lines, but the one I'll be talking about today is on data centers. Right. So now comes a bit of the grueling bit. I'll try to make this as fast as possible, but I swear this is going to be useful for everyone. Um, so the general GenX model works, as I mentioned, very similarly to Macro and to TEPES, wherein we're trying to minimize a system with the lowest possible cost. And I'm simplifying things here, but essentially the things that we want to simplify are investments in generation, fixed costs of generation, and the variable cost of generation. And I'm color coding these because it's going to be useful later on when we're seeing how data center flexibility affects your entire system. And another reason why I color coded it is just so you can see which portions of the formulation are actually, which ones correspond to which costs, right? So you have your new capacity investments, you have the fixed cost for your existing capacity minus whatever you retire as capacity. And a very critical component here is actually this purple part, which is the variable cost of generation. So this is essentially saying, I'm going to be deciding for every generator, for every hour, how much I'm going to turn on this generator and provide power to my grid, right? And the idea of the capacity expansion model is that we're trying to get the lowest possible cost subject to a bunch of constraints. And I want to say that these are going to be some of the most important ones. The first one, which is what drives this capacity expansion, is what's called the power balance constraint. So it says that all of the generation that we have should be equal to the demand of a system, right? And that's just this one. The purple generation is equal to this blue demand term for every hour, right? So you can see how in the cost function, that purple part there, right, is influenced by this constraint. So whatever happens to that purple part, this constraint here for power balance has to be satisfied. At the same time, you have here the purple part again, right, on the left-hand side, generation, right? It should be less than or equal to how much capacity you have, and quite importantly, this portion here called availability, right? Now, this availability is also what drives the investments, because you can think of this as a spectrum from 0 to 1. And what type of generation has an availability of spectrum from 0 to 1, hour to hour? Well, that's just your renewable resources, solar and wind, right? So whenever you change, or your decisions to change this generation from hour to hour are also influenced by the availability of certain types of resources, which also influence the total cost, right? So now we're getting a sense of how our decisions on capacity investments and generation are gonna influence the cost, right? And finally, there are some ramping constraints or operating constraints for generators. Now, there's a bunch of them. I'm just putting some of them here, right? So I hope that's clear. So what I want to point out next is, given that we have this model, this capacity expansion model, a simple one at that, which looks at being able to satisfy total generation and demand, right? How do we look at data centers in the grid, not just in the US, but anywhere in the world, right? And how does that influence this model, right? All of the talks around, data centers look at the way it increases demand, right? And so in this formulation, what is influenced by data centers is actually this portion here, the power balance constraint, right? You have your other demand, which we lump together, and you have the data center demand, which could increase or decrease and whatnot, right? And again, because we said that the change in the change because this power balance constraint needs to be satisfied, right? Then that decision in purple, right, also needs to change, which also changes the new capacity, which changes the existing capacity, which changes the retired capacity. And now this is sort of a reflection of what's happening in the real world, right? An increase in data center load leads to non-retirements of plants, leads to more investments in solar, wind, natural gas, non-retirement of coal, right? You can also have an increase in cost, which translates to an increase in cost for ratepayers. So GenX and these types of models, TEPES, Macro, really good at trying to model, system-level impacts of data centers. But the problem still is, well, this is just your typical data center without flexibility. How do we model flexibility now? Well, from our perspective, again, like this is just from the author's perspective and our conversations with data center providers, we look at two dimensions of flexibility, what we call the shifting horizon and the share of flexible workload, right? So the shifting horizon is just how much you can advance or delay data center load, right? From 0 to 24 hours. And actually, we modeled a delay in advance of up to a month, but there's no difference in the results if you model a month and 24 hours. So we just stuck with 24 hours. And the second is the share of flexible workload, which is the amount of data center load that can be moved to another hour, right? So when we were talking to data center providers, we asked them, so how much of your data center load is flexible? And they said, well, we can say that our data center load is flexible, but we can't tell you how much of it is flexible. And that ended the conversation, right? So our approach there is, if we don't know how flexible data center load is, we'll just model all the entire spectrum of flexibility from 1 to 100%, right? And so our modeling is really just 0 to 24 hours by 1 to 100% combinations of flexibility for data centers. So how does that work? We have here a graph which represents a stylized data center with capacity utilization of 80%. So remember my graph a while ago around 80% capacity utilization, right? On the x-axis, you have hours from 12 midnight, let's say, to 11 p.m. On the y-axis, you have normalized capacity of a data center from 0% to 100%. So that horizontal solid line is 100% capacity utilization, and this horizontal dashed line is 80% capacity utilization, right? So this is what we say in a very stylized way, what a typical data center capacity utilization would look like. If we insert data center temporal flexibility, let's say we take this load in hour 6, and we say that we have data center flexibility of 25% share of flexible workload and a shifting horizon of 6 hours, then as a data center owner, I can conceivably, if it's beneficial for me cost-wise, shift down a certain amount of load from hour 6 and move it somewhere else along this shifting horizon, right? And I don't even need to shift this all in just 1 hour, right? I can move it like this, hour 11 and hour 12. As long as I have that capacity on top, and as long as it's within the shifting horizon. Furthermore, if I have 100% share of flexible workload, then that means I can drop off everything here and just allocate that to where it's going to be feasible in my parameters. So again, we're not saying that all data centers are like this. There might be some, right? And what we're modeling is all possible combinations of flexibility. 0 to 24 hours, 1 to 100%. And it's up to data centers to decide what type of flexibility or what level of flexibility they have, right? Okay, going back to our model. Again, data center load affects their power balance constraint, which affects everything else. So how do we model temporal flexibility here? Well, the way we model it is by adding these two variables. Uh, I'm, I understand we want to go into the results, but again, please bear with me. Uh, these two variables are essentially saying what amount of data center load I'm going to be satisfying now, right? Minus what amount of data center load I'm going to be satisfying at another time period, right? So these two, along with constraints that I'm going to be introducing later on, will model temporal flexibility, right? Yep.
The, when we're talking about time here, what is the time resolution that you're talking about?
So we're looking at an hour time resolution.
But then the Gen X model that you started,
Uh-huh.
you said it's expansion.
Yes. So I
Confused here.
yeah.
Like expansion, you talk about far future, but then you're going back to the RD level resolution.
Yep. So I should have clarified that. So the Gen X model forecasts a future grid. So here we're forecasting, I believe, 2035, or yeah, something like that. But we're forecasting a 2035 future at an hourly resolution. So 8,760 hours of 2035.
So what is the difference between no? So do you know what is your mix of the generation, or is it something that Gen X is going to tell you?
So we take inputs of existing generators. So this is from the EIA or wherever resource you're gonna get, and then based off of uh, this model here, right? The existing generators are represented by this existing capacity, right? This new capacity is something that GenX will tell you, right? Given parameters on cost, given parameters on availability, given parameters on demand, right? So what GenX is saying is this is what a 2035 grid will look like at an hourly resolution, and the amount of investments that you're going to make for every type of generation, right? Given that you've shown me that these are the available technologies, this is the demand, and these are the cost forecasts. Now, is it a perfect way of forecasting 2035? No, right? There are assumptions that you make, there are sensitivity analysis that you do, but it provides a good way to at least get a sense of where a certain grid is headed, given policies that you want to implement, given cost forecasts, given demand forecasts, right? It's a good way to at least have that view. Yep. I hope that answers the question. Yep. Okay. So we have here the revised power balance constraint. And the way we are able to model this data center load shifting is by introducing another variable called unsatisfied load. And this is the amount of shifted data center load that you have yet to match with generation, right? And this can be a positive or a negative number. So positive number if it's not yet satisfied in a particular period, and negative if you've advanced data center load. So not super gonna go into this, but we are able to model temporal flexibility by simply saying that, okay, the amount of data center load that you satisfy now, like over the next H periods, which is the shifting horizon, should be greater than how much unsatisfied load there is in a particular period. And then the amount of data center load that will be satisfied in another time over the next H periods should be greater than or equal to the negative of unsatisfied loads. And we can talk about this in more detail after the presentation, but this is where I want folks to trust me that the model works, at least for now. If you have any skepticism, we welcome it. If there's better ways to model it, we also welcome it, because it takes a lot of time to run these models. So please let me know. All right, so we are now able to model data center temporal flexibility. let's go to the research portion. So what we did was, and I believe someone from the audience asked a while ago, like, most of the data centers are focused in one or two regions, right? And from our perspective, that's also where we want to concentrate our analysis, right? We looked at three regions in particular that correspond to 82% of projected data center load. That's Texas, the Mid-Atlantic, and the Western Interconnect, right? So, and I should say this is publicly available data from EPRI. So if you have questions on where to get that, EPRI has that data set. And so the purple also represents data center load. It's just that they're at different, they're much smaller in terms of scale compared to the yellow ones. So like the smallest yellow circle is 50 terawatt hours, and the largest purple one is 6 terawatt hours. So if we made this into yellow, it wouldn't even appear on the map. So we just wanted to make sure that it can be seen. Yep, yes?
I'm sorry if you already said this, but what are the borders on, like it's not state borders.
Yeah. So good observation. So the borders here are what's called IPM regions. So IPM regions are what are used by the EPA. I'm not sure if there's any. I want to say like specific. For sure there's a specific region why they created the IPM regions. I'm just not sure why it's delineated as IPM regions. So the reason why we use the IPM regions is because it's easy to allocate where generators and transmission lines are based on IPM regions as opposed to state borders, right? So when we're modeling GenX, each of these borders will have a specific set of generators. Let's say, for example, like this portion of Texas has, X amount of wind, X amount of solar, and whatnot, and the other border, the other portion will have W amount of wind, Y amount of coal, and stuff like that. The lines here, the green lines, are aggregated transmission lines. So there are a lot more transmission lines there, but we just bunched them all together just to make it more visually appealing, I want to say. All right? Okay. So we looked at each of these regions, and we wanted to understand a bunch of things. The first one is, if there is temporal flexibility in data centers, how will data centers operate, right? The second would be, if there is data center temporal flexibility, what would be the cost and emissions impact on the system? And third is, how will the grid operate? All right? There are others you can ask, right? But those are the three that we focused on. So first is, what will happen to data center operations? Okay, so this is a summary of data center operations in the Mid-Atlantic. On the x-axis, you have day of the year from January 1 until December 31. On the y-axis, you have hour of the day from 12 midnight until 11 p.m., right? So every point here is going to be an hour of operation of a data center in the year 2035, projected, right? If you see a green color, let's start with the red. If you see a red color, it means data centers are shifting load out of a data center. And if you see a green color, it means data centers, it's the reverse. It's the reverse. If it's a green color, then data centers are shifting load out of that hour. And if it's a red color, data centers are shifting load into that hour, right? So this is for, I believe, 24-hour flexibility and 100% flexibility, right? So what's happening here? We see that if it has that full flexibility, what data centers will do is actually shift out their load in the evening, right? And put it in the middle of the day, right? Also, out of the early morning, right? And into the middle of the day or somewhere early in the morning, right? And as we'll find out later on, the reason why this is the case is twofold, right? The first one is because of solar, right? There's a lot of solar in the middle of the day. And interestingly, the second one is because of thermal plants. And we'll get into that in the next couple of slides. But the idea is data centers are going to shift their load so that it flattens the net load curve of a system, right? What's the net load curve? The net load curve is all of the load that you have to satisfy using thermal plants, right? So it's your load minus your renewables minus your imports and exports, or net of imports and exports. So it's all the load that needs to get satisfied by thermal plants, right? So what data center flexibility does, I'll emphasize that, is it shifts load to flatten your net load curve, right? Okay. Next portion, which is what's the impact on cost and emissions? So these are again heat maps. Each column is a region that we examined: Mid-Atlantic, Texas, Western Interconnect. The first row is cost. The second row is emissions. So this is a percentage reduction in cost and emissions for every region relative to not having any temporal flexibility, right? Each one here is a combination of flexibility. X-axis is from 0 to 100% share of flexible workload. This one is 0 to 24 hours of a shifting horizon. So every combination is going to be a type or a level of flexibility of data centers, right? And the last thing I will point out, if you have a red color here, it means that your cost and emissions reduction are lower. And if you have a green color, it means that your cost and emissions reduction are higher, right? You can imagine that as you move from a lower left point to an upper right point, it means that you're moving from a data center that is inflexible to one that is more flexible. And this is my point also a while ago of saying, if I'm a data center and I don't want to share what level of flexibility I have, I'll just look at this and say, what's my contribution based on what my level of flexibility is, right? So what are our results here? Well, the first one is on cost, where we found from our perspective, it's intuitive that if you increase the temporal flexibility of a data center, then you will always have lower cost. And we think that just makes sense, because if your mandate is to find the lowest cost possible, then having that flexibility or having the ability to move or to find where the cheapest power is will always lead to lower cost, right? So that's well and good. But we also found this second non-intuitive result, which is that as you increase flexibility, it's not always the case that you have emissions reduction, right? You do have emissions reduction in Texas, for example, which has high emissions reduction of like 30 and 40% at the highest levels of flexibility. But you also have scenarios here in the Mid-Atlantic where higher flexibility, I don't know if this is clear, but this is negative 2% and negative 3%, meaning there's a 2% and a 3% increase in emissions as you increase your flexibility. Now, why is that? So I mentioned a while ago that the data centers will move their load from, those high net load hours to low net load hours. And it turns out that when this is the case, it actually helps the economic viability of certain fossil plants, right, or certain thermal plants, coal in particular, in the Mid-Atlantic, right? And to see that, we have here this operations. This is the operations of an average summer day in the Mid-Atlantic. Yes?
If you go back one slide, for the best part, best energy section.
This one here?
Yeah. What is happening there? So I can see that is 1% increase, and then you have a sudden jump.
Yeah, so this is a 1% decrease in emissions. Yep. So I think this is just like I want to say it's a modeling quirk, but essentially, I don't have a good answer for you, but good question. We should investigate that. Yep.
This
Yes.
is the granularity of the heat maps. So you are observing 100 points in the x-axis and 2400 or so. Okay.
Yep. Exactly. So it's yeah. So
This is a linear programming model. So
yes.
or
Yes. So it's reaching optimality. So it's also fairly fast because well, not I want to say relatively fast because it's linear programming, but still quite takes quite some time. So we had to run this for like a month or so to finish all of the scenarios. So it's uh, 24 by 100 by 3. And then we had to model a lot of sensitivity scenarios. So I want to say by another 10 or 15,
You're in the order of hundreds of thousands.
something like that. So, but that's the
and the CO2 emission cost is included in the objective function.
so no. So that's so in this particular result that we have, we didn't put in the CO2 emissions cost. So if we did, which we actually have some sensitivity analysis on that, then you would see emissions reduction with flexibility. So this is really just if you're looking at a system that minimizes just operational and investment costs. We don't have any CO2 policies in this result. Yep.
May I ask something just before you continue?
Mm-hmm.
To fully understand, the flexibility that you're modeling implies that if in 1 hour you decide to decrease your consumption and allocate that consumption within the next 24 hours, this means that at the end of the year, your total consumption is going to be the same?
Yes.
So you're not going to sacrifice energy in some hours if needed for the system or if, okay, so the net value is the same.
Yes. So the total load for the entire system stays the same within for the whole year. It's just that the profile changes.
Like a demand response,
Exactly. Exactly.
demand-side management.
Yes. Yes. Exactly. That's exactly what it is. I think the main difference here is just because of the magnitude of the amount of load that we analyze, and what we're trying to see is just all of these combinations, like seeing what different combinations would lead to certain types of improvements, what changes in operations will happen. And there are some similarities with existing research around EV chargers, which come to very similar conclusions, but the magnitude of that impact is quite small compared to this. Yep.
I'm wondering whether in a real setting,
Mhm.
the data center, if prices are very high,
Mhm.
might decide to, well, not carry out some processes, some IT processes, if this results in something that is not beneficial from, so
Yep.
not only shifting but also canceling or sending that workload to another.
Yes. So that's a very good research question, which we are currently pursuing in an extension to this work. So in that extension, we're actually comparing multiple strategies from a data center's perspective. We're looking at temporal flexibility. We're looking at spatial flexibility. So what you mentioned around if the prices are high, it's going to move it to another part of the US, or maybe, well, we're modeling the US, but it's worldwide, right? The third one is bringing your own capacity. So like if they know that this is what's going to happen in the future because of certain price signals, can they actually invest, the data centers, invest in their own generation? Solar, wind, batteries, natural gas. Yep. And what's that going to do to your system? So that one is a bit more complex, but we've developed a system to try and model that. We're still trying to verify that. The other one is if they can invest in the grid instead. What if they can build transmission lines? So moving power instead of spatial flexibility. right? There's also energy efficiency. What if they don't need to use that same amount of energy, right, with DeepSeek and whatnot. So that that extension is really a comparison of all of these strategies that data centers can have. Yep. Any other questions? Okay. So as I mentioned a while ago, so these are the operations of a typical summer day in the Mid-Atlantic. So x-axis is 12 midnight until 11 p.m. Y-axis is power generation. I think this should be in megawatt hours. And each of these colors represent a technology, and I'm highlighting coal, natural gas. The yellow one is solar. The blue one is wind. This orange one is nuclear. So I should also point out, this green dashed line is your inflexible data center load. The red dashed line is your net load. So net load is the total amount of load that needs to get satisfied by thermal resources. Here on the right is your 24-hour 100% flexibility. So no flexibility, 24-hour 100% flexibility. You still have, just as a reference, this portion of inflexible load, but you have this flexible data center load, which is the solid line in green, and the corresponding solid line in red, which is the net load when you have data center temporal flexibility. And as I mentioned a while ago, what data center temporal flexibility does is it flattens that net load curve, right? You see the red dashed line? The red dashed line, it flattens it. And this one here in the middle, the red dashed line moves up. And so the variance across the day sort of diminishes, right? And it's not as clear here, but you can see that coal operations have less ramping, right? Here, coal operations are flatter, right? And that's actually what leads to this increase in emissions when you have higher flexibility in the Mid-Atlantic, which naturally leads to the question, why is this unique to the Mid-Atlantic? Why is it that in other regions you have emissions reduction when you have higher flexibility? It turns out, and this is where the policy hat gets put on, it's all about support for certain types of technologies. And this is also tied to what I showed before I showed this PowerPoint, which is if you have a certain support for a type of technology, then the results of this research will come to fruition for one or the other. And we'll show you an example of that. I want us to remember this case of Texas, where if you don't have any restrictions, then temporal flexibility will actually reduce emissions, right? Well, we examined a scenario where what if the cost of building renewables is going to be higher? What if there is a lot of disapproval against renewables? A lot of what ifs, but that's what modeling allows us to do. In this case, what we're seeing is, well, I first have to say what these graphs are. So these are your generation from different types of technologies, wherein each bar is a cost multiplier to renewables. So if renewables are standard, 1 times the cost, and then 1.1 times the cost, 1.2, 1.3, 1.4, and 1.5. So progressively making renewables more expensive, right? Which you could translate as, support for renewables and whatnot. Other interpretations can also be included. As renewables get more expensive or more prohibitive, right, we see that the share of wind and solar decreases, which makes sense. More expensive renewables, it means less investments in that type of technology, means less generation from those types of technologies as well. But if we look at this portion here, right, this is emissions. Again, cost multiplier, x-axis 1 to 2, and then the y-axis is CO2 emissions. At some point, if you increase the cost of renewables or make it more difficult to build renewables, then having more flexibility also increases your emissions. Same as what's been happening in the Mid-Atlantic. And so we have this interpretation around, data center flexibility, temporal flexibility is good, right? On the cost side. On the emissions, there's always that, what is the accompanying policy that will lead to certain types of emissions results. Mm-hmm.
The reasoning behind, I mean, how being more flexible. Well, it's true that the emissions is not in the objective function.
Yes.
That you are not
Yes.
penalizing.
Mhm.
So, but being more flexible means that your objective function should be lower because you are relaxing.
Correct.
So you're relaxing the problem. You are getting a cheaper solution.
Mhm.
But when you analyze, the emissions are higher because of the flexibility. Why? I mean, where is the
So it's the reason why I put this ramping constraint here. So it doesn't look like it from the operations a while ago, the operational graph a while.
flexibility for the data center? This means that the ramping of the net load provided by thermal generators is more demanding.
But it's flatter.
So if you introduce flexibility in the system, I guess that you are allowing more cheaper generation, coal in this case, to produce more.
Yes.
Otherwise, coal was restricted by the ramps.
Yes. Coal is
Flexibilizing the system, and therefore coal can produce more because
And you're assuming that coal is cheaper in terms of the variable cost, but
I
with
guess
more
it's the-
emissions.
in some assumption. Yes. 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 Yeah. Yep. So I have maybe like 2 minutes, but I'm already at my last slide. Yes?
I was just wondering why emissions go up in the Western interconnect, because it seems like you would have solar there.
So it doesn't go up in the Western interconnect. It reduces by like 1 to 2%. Yeah.
Right?
Yes. I think it's because of like just the amount of data centers relative to everywhere else. Right? So like there is data center load, but like it's not as large as
you're increasing the demand by, let's say, 5%, you're assuming that the costs are only associated to half of that production, you are going to expect only a 5% increase in the total cost, total operational cost. So that's why it's not necessarily increasing by the amount of demand you are, because you are guessing, I'm guessing that you are satisfying partially the demand with renewable technology.
Yep. Exactly. Mm-hmm. Yep. So just to finish things off, what did we cover in 1 hour? We covered data center flexibility, how we model temporal flexibility, and the impacts of data center flexibility on the grid. So thank you. If you have any questions, just let me know. My email is here. We're in the CPR office in E19. So thank you so much.
We have time for questions.
Yes, yes.
But my question is more technical actually.
Uh-huh.
It is more about the way that when you are doing your optimization, in every optimization loop, where is your computational cost coming from? Is it from your simulation or the optimizer?
It's from the optimizer.
So simulations are quite fast to run.
So in this case, the simulation is, so there is no simulation. It's the entire thing is an optimizer, right? Because when you're looking at this problem, the decisions, right, are all part of the optimizer, and those decisions are what we plot.
Oh, I get it.
Yeah. Yes?
Can
you chain the ball to optimize emission reductions instead, and the extra cost can be taken by some policy decision by either road building data center?
You can minimize emissions by incorporating either a carbon price or having an emissions cap. So I want us to think about if we try to minimize emissions as the sole objective function, then you're not going to build anything. Yeah, because like that means your your objective is, as long as it's so expensive, you, yeah, it's fine. Yeah. Any other questions? Yep.
And for the consumption of the data center, given that you're modeling hour by hour, is there any RAM constraint, or can it go from 100% till 80%?
So I get, yeah. So we do not have any data center operation restrictions, which is actually one of the, I guess, like comments on our work. So those who have read the work said, well, you have to incorporate those ramping constraints for data centers if you are looking at ramping constraints of on the power system side. Yes.
But at the same time, this is a very aggregate
Yes.
consumption, so maybe one.
So yeah, so I guess like as a preview of like the subsequent research that we're trying to do here, we're trying to look at ownership structures within data centers. So for example, Amazon, throwing out a company out there, would have a data center, let's say in Texas, and then a data center in PJM, and their operations might be different compared to a data center network that's operated by Google, right? And the decisions on spatial and temporal flexibility, including the ones on deciding on what would be the prices, would be different in that case, right? So, yeah. Thank you.